today's topic. So what have we been doing? Let's just review a little bit. We've been doing confidence intervals, hypothesis testing, statistical testing. Based on this outcome, what can we learn about this one variable? All right. The next step is what can we learn about interactions between variables? So that is regressions and correlation analysis, right? If I know that somebody is 50 years old, how does that change their body mass index? Or how does that change their income? Or how does that change, right? What's the correlation? It's not causality. It's not that age causes you to be rich or heavy or something. But what's the correlation between random variables? So we need to understand, so our next topic is regression analysis, correlation analysis, which is the interdependence of variables. And again, statistics is dual to probability. In the sense that probability takes distributions, known distributions, and converts them into outcomes. If this is the distribution, this is what you expect to see. And statistics goes the other way, right? If we've seen some outcome, what can we infer about the distribution? So now we want to understand if we've seen certain outcomes about what can we infer about the correlation between the random variables that we were observing. Okay? So we need to spend a little bit more time on this side of things. We're gonna. It's been a while since we talked about conditional probability, and we need to have that solidly within our grasp in order to go the other way from outcomes to distributions. So let's just recall. Do we remember what conditional expectations and conditional densities and conditional probabilities are? These are the things that we're going to need. So what is what's the conditional probability? So let's say the probability distribution f sub y of y given the knowledge of the value of x. So this is a conditional density, probability density of y knowing the value of x. In other words, I have some fxy, some joint probability density. This is the joint probability density. So this is the probability that in a neighborhood of little x and a neighborhood of little y that you find the random variables having that value. So given the joint probability density, how can we recover the conditional density of y given the value of x?
The joint over the marginal.
Exactly. So it's the joint distribution. What's the probability that you saw this value of x and y renormalized relative to the probability of seeing this value at all, divided by the marginal fx of x. And what is the marginal? The marginal density fx of x.
The integral of the joint.
Right. Integrate out the other variable. Take the joint distribution, integrate out the other variable. All of this is ringing bells, I hope? And do you understand it geometrically what's going on as areas and volumes? So if you have some, let's call this the x-axis and the y-axis, and here's the joint fxy. So this is some curve. I don't know what it looks like. Maybe it looks like this. Some surface, rather. Okay, maybe it's only supported in the positive reals. So in the positive reals in x and the positive reals in y, it has some curve sitting above the xy plane. Okay? The total volume under that curve is 1. Okay, that's what it means to be a probability density function. It's a joint probability density function, but it's still a probability density function, so its total mass is 1. And then if I want to take all of these, I mean, it's not easy to draw surfaces, hopefully you see that that's like a blanket over top of x and y. The volume under that blanket is 1. That's the total probability of everything, of all possible outcomes. The marginal density is you fix a value of little x. So I fix a particular value of little x. Here's a particular value of little x. And then so now I get a curve. That curve, the area under that curve, just straight down, it's not a volume anymore, it's not a 3D measurement, it's an area. The area under that curve, well, it's some number. And that number will be less than 1, typically, because the total volume needs to be 1. But we're going to restrict our world, the conditional density is restrict our world to the case where x is equal to little x. If we saw little x as the outcome for x, then we already know that we're here. We don't need to worry about the entire space of possible outcomes. We already know that we're restricted to this plane, x equals x. And in that plane, let's renormalize this density by saying, well, what probability distribution do we have on y? It's just the original probability distribution that we had on x and y, with little x being fixed, but I have to renormalize to make it a probability distribution. So if I take this entire integral, that marginal value will be some value. I mean, I'll arbitrarily plot it here in the same plane. So this is the value fx of x. In fact, there's a whole function fx of x, which is sort of how likely is the x variable when we integrate out the y variable. And then that value will renormalize this ratio to be a probability density function. Okay? Hopefully that's clear. Should we do some examples just to see how clear this is? Yes. Some people say no, but some people say yes.
I like to just think of it as like Bayes' theorem.
Yes, exactly. This is Bayesian. What's the probability of the intersection? So, right, this is the probability of event A given an event B. Well, you can take this as the definition. It's the probability of the intersection of the events normalized relative to the fact that B, this is the probability of A given B. So given that we know that B happened, let's renormalize the probability to be the intersection of everything with B relative to the probability that B happened. Okay? Let's do a couple of, okay, so that's conditional density, and then we can do conditional expectation. So that was the conditional density function. And then conditional expectation so this is the expectation of a random variable y given knowledge that the random variable x, given knowledge of the random variable x, which let me write as given that we know what value the random variable x has taken. Yes?
In the picture, the f's of x,
Yes, I'm drawing it in an arbitrary, it doesn't really belong in the same plane.
right.
It should be somewhere else as a new graph. But what I'm saying is if you collapse all the mass, let's say, onto the x-axis, there's no particular place to collapse it to. You could collapse it to some other picture. But if you wanted to, you could collapse it in the same picture so that you can keep the same x-axis. Then now it becomes a function in the xz plane whose height is the marginal density. Does that make sense? And then you could do the same thing in the y direction. You could collapse all the mass of x onto the yz plane, and then you get another curve here, which is the y marginal. And where we're taking a conditional distribution, we're slicing by a plane at this point, big X is equal to little x. We see some curve here, but that curve doesn't have total integral 1. And the thing that we need to divide by to restore the probability, it being a probability density, is to divide by exactly the value of this marginal.
Oh, so the thing that you drew with the shaded curve, that's f sub x, y.
Yes, so the shaded curve is exactly the values of x, well, the curve is the values of x sub, is just the joint
Right.
probability density. And then all I was saying, I shaded under it to illustrate the area under that curve. So that area will not necessarily be 1. We need to renormalize by the marginal to make this a probability density. Okay? Any questions? All right. So what is conditional expectation? How do I compute the expected value of y knowing the value of x? This is the thing. These somehow densities, conditional densities, are not so complicated, but conditional expectations are. We'll do a couple of examples to get people more accustomed. We talked about this in week 1, and there's been many weeks since then that we haven't needed it, so I don't expect you to necessarily remember. Yes?
Isn't the integral of y times the conditional density?
Exactly. It's what you should think it should be. The probability density of some variable is the value of that variable times the probability that that variable happens. But in this case, the probability that that variable happens is the conditional density. Y, given that we know the value of x, dy. And this ranges over, let me write y here, which is just the range of y. So I'm abusing notation a little bit. There's the random variable y, and then there's the range of values that y takes. Is that okay if I abuse notation? So let's do some examples. And the most basic example I like to think of is something you can hold in your hands. So x and y are IID dice. So I'm rolling 2 dice. Okay? So they take values. So what's the joint density? F, x, y will look like, here are the possible values of x and y, 1, 2, 3, 4, 5, 6. The possible values of y are 1, 2, 3, 4, 5, 6. Okay, so this is my x, y, or rather x, y. Let me even change the variables so that it looks like the other picture that we had. Here's my x direction, here's my y direction, and now here's my z direction. So what is this surface above the possible values? Of course, now this is a discrete random variable instead of a continuous random variable, but we can still plot it in the same way. What's the surface? It's just flat. The surface, there's no fluctuation, everything has equal probability, and it's a flat surface at height 1 over 36. Okay? So what you should think of is, here's my x-axis, here's my y-axis. What is fxy? For every single point in 1 through 6, its value is 1 over 36. Okay, so all of these are 1 over 36. Okay, so if you're thinking in the x, y plane, then the function fxy is not very interesting. You take this height 1 over 36 and you put this plane at height 1 over 36 above her. For all the values 1 through 6. 1 through 6 and 1 through 6. Does that make sense? So nothing happened. There's nothing interesting going on. Let's take the pair of random variables. So, by the way, what's the conditional? If 2 random variables are independent, what's the conditional expectation? Right. If x and y are independent, why? Why is that true? Why do you just recover the expected value of y?
We have the top and the bottom.
Right. If they're independent, look at what happens if they're independent. If they're independent, then this graph is just a product of 2 graphs. There's a graph for the marginal of x, there's a graph for the marginal of y. You take the values of the 2, you multiply them, that gives you the value of the joint. That's what it means to be independent. And so the probability of this is the marginal at x times the marginal of y divided by the marginal of x. So the conditional distribution of y given x is just the marginal distribution. That's what it means to be independent. So this is just the marginal distribution of y, and the integral of y dy is the expected value of y. It's literally what the expected value is. Does everyone, did I say that too fast? Everybody follow that? Okay. So now let's make things more interesting. So this was kind of not a great example because we're not going to learn anything. This is just a flat curve. There's no, the conditional expectation is going to be boring. What is the expected value of one of these random variables? 3/2, right? This adds to 7, this adds to 7, that adds to 7, and there's 6 of them. So the average value, so the expected value of x is 3.5, 7/2. So now let's make things interesting. Let z be the sum of the variables. Now we have a slightly more interesting distribution. Look at what is the joint density function of x and z together. And let's compute all of the conditional expectations and the marginals. So what is this? The possible values, let me again put x on the down axis, z on the across axis. The possible values of x are 1 through 6, 1, 2, 3, 4, 5, 6. The possible values of z are 2 to 12, right? We're adding numbers from 1 to 6. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the possible values of z. So this is our space of outcomes. 1 through 6 in x, 2 through 12 in z. So again, you should have a picture like this in mind, and let's put that picture in our minds. So here's the x direction from 1 through 6. Here's the z direction from 2 to 12 in z, and the height will be f of xz. Okay. What values do I put in here? So the outcome, x is equal to 1, z is equal to 2, occurs with what probability? 1 over 36, because if z is equal to 2, how do I roll 2 dice and get 2? Snake eyes, right? 1 and 1. Okay? So 2, 1 happens with probability 1 over 36. How about 2, 2? What's the probability of 2, 2? 1 over 36 again. No, it's 0. There's no way to get x equals 2 if z is 2, because y can't be 0. Okay? So these are zeros. So zeros I just won't put anything in. Well, I'll put zeros for now, but... Okay? There's no way, if z is equal to 2, to get any value of x except for 1. In fact, it should be clear, if we know both the value of z and x, that completely determines the value of y. And so all of these, so these outcomes are completely determining y. How about x is 1 and z is 3? 2 over 36. If z is 3 and x is 1, then y is 2, and there's exactly one way for x to be 1 and y to be 2. So only 1 out of the 36 outcomes gives you this.
But yeah, so whenever it's non-zero, it's 1 out of 36, right?
Exactly.
Yeah.
Because of what I said before, that you've determined the values of x and y once you've determined the values of x and z. So they're always going to be 1 over 36s. So let me just put a dot whenever there's a 1 over 36 and nothing when there isn't. So I don't have to write 1 over 36 every time. Dot equals 1 over 36. How about 2 and 3? Can't have 2 and 3, right? Can't happen? Oh, it can if x is 2 and y is 1, which happens 1 over 36 of the time. Okay. But 3 and 3 can't happen. So these I'm going to put nothing in. Okay? Nothing equals 0. Nothing equals 0. So this is 0, 0. How about 4 and 1? 1 over 36, 4 and 2. 1 over 36, 4 and 3. 1 over 36, 4 and 4. 1 over 36, 0. Okay, so it doesn't happen here. How about 5? We can get up to x equals 4, but not higher. How about 6? We can get up to x equals 5, but not higher. How about 7? We can get up to x equals 6. These are looking like zeros. These are meant to be dots. These are all dots. Dots meaning 1 over 36 and nothing else elsewhere.
Put a line through the zero.
Just put a line. a line through the zeros like this. Like this can't happen. Okay, 8, now I get all values from here on out. For 8, I can see all values.
No, if you get a 1, you certainly.
I can't see a 1, because then y would have to be 7. So now, you see the pattern, right? You see the pattern? I can't get a 1 anymore. And now, once z is 9, I can't get a 2. And once it's a 10, I can't get those. And that. Something happened in my picture. By the time I'm at 12, I should just be at 6. 8, I can't get a 1. 9, 10.
You put the dots in the
Whoops.
wrong place.
I put the dots in the wrong place?
No,
the last dot.
the last dot, move it down.
Yes, thank you. That's not a dot. It's just that last dot. Good. Yeah, it's a parallelogram. Okay? So I hope you kind of see what happened. In this picture, we went sort of, they're all at height 1 over 36, but it's not a whole square. It's a parallelogram. I mean, as you should expect it to be, because it's taking the basis vectors 0, 1, and 1, 0 and adding 2 of them. Okay? So it's not so surprising geometrically that what we're seeing, let's see if I can even draw this, is something like, oh gosh, this is not easy to draw. Goes out to 6 and then, I need to take the course in perspective drawing or something. But it's something like this. Wow, this is hard. Okay, this was going to go here, and this is going to be like that, and maybe like that, something like that. It's a parallelogram at height 1 over 36. Hopefully you can see geometrically, 1 over 36. And the point is it's 0 after that. It's 0 in this triangle, and it's 0 down in this triangle. Okay, so it's 0, and then we raise up to height 1 over 36, and this is the parallelogram. What are the marginal distributions? What's the marginal distribution of x? So let's put that here. F sub x of x. Bless you. So I collapse all of these probabilities onto some axis. I guess I was collapsing it onto the x-axis, but it doesn't matter where you draw your marginals. What's the marginal distribution of x? Right, because it's 136 and I have 6 of them. And then it's 1 over 36 and I have 6 of them. And that happens for every single row. So this happens with probability 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Of course it should. Right? X was just a roll of a die. It has to be 1, 6. All right. Let's check the marginal of z. So the marginal of z, depending on the value of z, will be, well, there are 12 values, so it'll be 1/12. Actually, there's only 11 values, it'll be 1/11. No. This is a real marginal. I have 1 over 36 chances of seeing a 2. 1 over 36. Here I get 2 over 36. 2 over 36. 3 over 36. 4, 5, 6. And then it comes back down. 5, 4, 3, 2, 1. All of these are over 36. Does everybody follow? These are the marginal distributions of z. So the probability that z comes out to 4 is 3/36. Because there's 3 ways for z to come out to 4. You can have 1 and 2, 2 and 2, 1 and 3, 2 and 2, or 3 and 1. Does that make sense? All right, here's the fun part. So we've computed, so we're basically started with a joint density. We've computed the marginals. Now let's compute the conditional expectations. So what just happened? I pushed the button. Yeah. No. Help. There we go. Okay, we're back. All right, we're back. Sorry about that. Technical difficulties. So what is the expected value of x given that we know what z is? Given the value of z, what is the expected value of x? What's that? There is a formula. We're going to figure out what that formula is. Let's try to figure out what that formula is. Okay? So, remember what this is. We're going to take the value, so this is an integral. Of course, integral here means sum, over the possible values of x from 1 through 6. We're going to take that value, and we'll multiply it by the conditional probability. Okay, so this is the joint probability of x and z, of seeing that value of x and this fixed value of z, divided by the probability that we saw that fixed value of z. And that's an integral dx. That's a sum over the values of x. So let's do some examples. Okay, so let's do a table of this. So here's the expected value. So here's the possible values of z. Z ranges from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A priori, there's no reason for there to be a nice formula for this, I suppose. And then here, let's put what the expected value of x given the value of z is. Okay, everybody see this table? So, if z is equal to 2, what's the marginal? 1 over 36. What are the possible values of x for which this joint density function is non-zero? Only x equals 1. All the other ones will give you a 0. So you get a value of 1 over 36 divided by 1 over 36 times 1. 1. Does everybody see that? Does everybody see how we got 1 there? This value, I don't want to screw up this formula. We had a sum over the values of x times these. Well, okay, that one was a little too trivial. Let's do the next one. Let's say z is equal to 3. What is the denominator here? If z is equal to 3, our marginal density value is 2 over 36. So the denominator will be 2 over 36 everywhere. We have two possible numerators. One numerator is when x is equal to 1, which happens with probability 1 over 36. So there's a 1 over 36. The other possibility is that x is equal to 2, and that happens with probability 1 over 36. Does everybody see that? This is a value of x equal to 1 times the probability with which that happens, given that z is equal to 3, which is 1 over 36, plus the value of x being 2 times this density, which is 1 over 36. And all of that is divided by the probability, the marginal probability of z, which is 2 over 36. Does that make sense? We can simplify this. The 1 over 36's all die. I have 1 plus 2 divided by 2. That's 3 halves. 1 1/2. Okay? It's 1 1/2.
But because they're equally likely, you're just averaging the possible x's, right?
I'm averaging them, but weighted by the value that they take. That's the expected value of x.
Oh, right.
They are equally likely. These will all be 1 over 36's. You're seeing that pattern.
Yeah.
But this will be the values that they take.
Yeah.
Okay? So what about for 4? Let's make a little more room here for 4. We're going to have the value 1. How often does the value x equals 1 and z equal 4 happen? 1 over 36 of the time, divided by what's the marginal value of z when z is equal to 4? 3 over 36. Plus, when x is equal to 2, that happens with 1 over 36 divided by 3 over 36. And when x is equal to 3, that happens with 1 over 36 divided by the marginal 3 over 36. The 1 over 36's, as always, will cancel. I have a 1 plus 2 plus 3 divided by 3. It's 2. So this value is 2.
But again, that's just the average.
It's the weighted average. It's the average of the values weighted by the values that they take. Right? I'm multiplying x by,
But the number of weights can happen. Yes.
say it again?
Yeah, it's weighted by the number of weights can happen.
It's weighted by the weight of the value. Like x is the value, 3.
Yeah. No, we're just saying if you consider the numbers 1, 2, 3, their averages.
Their average, yes, exactly. It's the average of those values.
But
Yep.
that's only happening because the probability is the same for all of them.
Yeah,
That's
it's
happening because the probabilities of all of them are the same. Yeah.
Yeah.
Okay. Exercise. So we have a pattern. 1, 1.5, 2, 2.5, 3, and so on. Actually, what's the pattern? So you guys can continue this if you want to check more of this with exact numerics, you can. What is this expectation for any value of z? Z over 2. As a function of z, this function is z over 2. The expected value of x as a conditioned on the value of z being little z is little z over 2. And if you think about it, of course it is. If you know what the sum of 2 dice rolls is, what should you guess for the expected value of one of them? Half the roll.
7.
What's that?
Z is 7. And the expected value of Z is 7.
If you take the value z is 7, yes, then any value is equally likely. That's the only row where we have all 6 possibilities.
So there you have independence in that column.
There you have complete independence in that one column. That's right. But as random variables, they're not independent. Yep. So in that one column, it's completely independent, and there you get your 3 halves, which is the true expected value of x, the original expected value of x. Okay? Does that make sense? One more question?
For, oh, okay. I think I was just looking at the wrong number, but what you did for, like, what you expanded there, you have
Here?
yeah, you have 3 over 36 in the denominator, because that's the marginal, yeah, probability.
So the question is, why do I have 3 over 36 everywhere in the denominator? That's the marginal probability of z equals 4.
And
3
then
over
the-
36.
The numerator is the joint probability of x equals.
The numerator is the joint probability. Yeah, so this is the conditional. I wrote out the conditional
Oh, yeah.
density as the joint density divided by the marginal density.
Right, okay.
Because that's the easiest thing to compute. I mean, we could have also computed all of the conditional densities but that's complicated because for each value of z, you get a conditional density, which is a function of x. So that's another matrix, another big matrix. Taylor.
Okay, so I know it was easy to find the conditional distribution kind of like you in the simple problem, but if you were doing something else, like
We're going to do
normally-
something else.
Oh, then okay. I was just gonna ask: do people usually find the like what the condition like a general formula for the conditional expectation by like going through all of the
No.
possible values, or they do like algebraic manipulation?
Yes, excellent question. The question was, do people find the, I mean, we saw a pattern and we guessed what the pattern was, and the pattern is true for the only cases that, there's finally many cases that matter, so it's true. That is not how you do mathematics. Yes, you're absolutely right. This is a very ad hoc method, and what we're going to do in a minute is do this algebraically with actual functions. But I find that when we do it algebraically with actual functions, we lose the meaning of what's going on. We start doing algebraic manipulations in calculus without understanding the underlying calculation. Okay? So we're going to do exactly what you're suggesting. So it's a great question.
Okay, thanks.
Okay? Let's do, before we do that, let's do one more. We took the expected value of z, conditional expectation of x, given the known value of z. Let's do the opposite. What is the expected value of z given the known value of x? Now this one's going to be a little bit easier. Well, let's do it a slightly different way. So here's an exercise for you at home. If you really want to, if you're feeling uneasy about this, exercise for your own understanding. Do exactly this and write and work out what this expectation is. Okay? Exercise. Work this out explicitly. let's get one more level of sophistication, which is not to work it out explicitly, but not quite go all the way to the algebraic level. Z, remember, is x plus y. And expectation is just an integral. Integrals are linear. So this is the expected value of x, given that we know that x is equal to little x, plus the expected value of y, given that we know that x is equal to little x. What is the expected value? What value do we expect from x if we know that x is little x? Little x. We've got this down to we know there's no randomness anymore. We got it down to a singleton, right? This must be little x. How about x and y? They're independent, so the conditional expectation is just the original expectation. The original expectation was 3.5. Okay? So the expected value of z as a function of x is x plus 3.5. In other words, we already know the value of x, so just add the expected value of y to it. That is the conditional expectation of z. Okay. Something very interesting happened in both of these cases. And let's see if I can show both of these cases. In both of these cases, both the conditional expectation of z with respect to x and the conditional expectation of x with respect to z, I said them backwards from where I pointed. In both cases, we get a linear function of the variable. So one thing to notice is this. Let me make this point very clear. The expectation, because you're taking an expectation, it feels like you're not getting a random variable, right? You're getting a scalar now. You're just getting a value. But a conditional expectation is a random variable. So let me note conditional expectation. I mean, it might be a trivial random variable. It might be a random variable that only takes one value. That's not a very interesting random variable. Conditional expectation is, in general at least, a random variable. It's not a number. This is a random variable. It's x. So a better way to write this, perhaps, is as a variable, the conditional expectation of z, given knowledge of capital X as a random variable, is capital X plus 3.5. Instead of going to what values, I mean, this is shorthand for if you know the value little x that capital X took, then what you do is you add 3.5 to it, and that gives you the conditional expectation. So this is itself a random variable. It's just that random variable added on by a scalar. So this is a linear relationship. So definition, random variables, let's see, how do I want to say this? The regression, I had a nonlinear example to show you first. Okay, I'll say a regression, which is just another word for conditional expectation. A regression, i.e. conditional expectation is linear if the expectation of a variable y given the value of x is a linear function in x, alpha plus beta x. Okay? Both of these were linear functions, this one and this one, if you can see that, are linear functions of the variable that it's getting conditioned on. Okay. Let's do exactly what Taylor wanted us to do. So let me give you something more interesting. So by the way, this is a bivariate regression. Bivariate as opposed to multivariate. Bivariate, two variables. Bivariate regression as opposed to multivariate regression. So let's compute the regression, or this is something called the regression equation. Regression equation. So find the bivariate regression equation for, where's my distribution, for y in terms of x, for y as a function of x, for this joint density. For this joint density, f of x, y of little x, little y is equal to x times e to the minus x times 1 plus y. That's if both x and y are positive and 0 otherwise. Okay? Let's find the regression equation of y on x. Find the regression equation of y on x. Let's say on x as a function of x. All right, that's our question. What is this? Again, we're in the positive quadrant. Let's draw this picture one last time. Here's the values of x and here's the values of y. I only care about positive values of x and positive values of y. Within those values, I don't know what I'm decaying in x. I'm also decaying in y, but I'm also decaying when x goes to 0, but not when y goes to 0. So I get something that looks like this, and here it looks like that. You sort of see this kind of blanket looking thing. So I'm decaying when x goes to 0. I'm tucked here. I'm going to 0 at infinity in the x. I'm drawing the picture the wrong way. When x goes to 0, I'm over there. When y goes to 0, I'm over here. But anyway, it doesn't matter. It's some curve over top of the quadrant. Yes?
Would multivariate regression be one random variable in terms of n random variables, or would it be n random variables in terms of one random?
So it can depend. We're about to do an example of one variable in terms of several.
Okay.
But absolutely, your age can determine a lot of things at the same time, right? Or given lots of factors, you get even more information about your income or whatever it is that you're trying to model. So it goes both ways. But let's start again at the beginning. We're still just doing probability theory. We're giving it a new name. We're giving conditional expectation the new name regression. But that's the only thing statistical that we're doing at the moment. Okay. Now, these random variables are actually independent, right? Because I have like x e to the minus x, and then I have a separate e to the minus 1 plus y. So those multiply and they separate. Thank you for shaking your head no. This is equal to x times, let's open this up. E to the minus x, that looks good, but then there's a factor of e to the minus xy. Hopefully this algebra is not going to catch anybody. This will never be a product of a function of x times a function of y. Right? It's in the exponent. So they're not independent. They're not independent. That's okay. We can still, so what are we trying to do? This regression equation, we're trying to compute, so sometimes this is written mu of y given x, y slash x. Let me try to use the same notation as the book just to not confuse you further. I had it here a second ago. Yeah, y slash x. Mu of y slash x is another word for the expected value of y given x. Okay, so in order to compute this, we need to integrate over y, little y, and then the marginal. And then the conditional probability, which is the joint of x and y divided by the marginal of x being whatever value it is, dy. So the first thing we need to do is we need to compute the marginal distribution. Okay, so step one, compute the marginal distribution density fx of x. So fx of x, what do we do to get fx of x? We integrate out the y variable. We collapse everything onto the x variable. Okay? So keeping the little x variable fixed for a particular value of little x, we integrate out over the range of the variable y, the value fxy of xy dy. Can everybody see that? So far, so good? All right, this is just calculus. The range of y is 0 to infinity. The value of the joint density is this. Let me break it up. It'll be more convenient. And I'm integrating dy. Can everybody see that? Everybody see that? I just put in the value that you can't see anymore. Actually, you can see it there, dy. What happens to this part? The constant pulls out. So this is x e to the minus x. How do I integrate e to the minus xy with respect to y? You have to do it by parts, and then no, it's just x is a constant. So the antiderivative exactly is negative 1 over x. And this is evaluated from 0 to infinity. At infinity, I get x is positive, so I get 0. Right? X is positive. Let's remember here that it's 0 unless x is positive. X is positive, so I get 0. And then minus the value at 0. What's the value at 0? There's this constant out front. And then the value of this at 0 is 1 over negative x. Also known as e to the minus x. X cancels on top and bottom. Okay? So in this picture, if I want to put the graph e to the minus x on this picture, here it is. Okay? So this is the marginal. Fx of x is e to the minus x. Again, there's no reason to put it there and not somewhere else, but let's just think about flattening onto that plane. Okay? If x had if y took both positive and negative values, then it would really be flattening onto that plane. And again, there's no reason to put it there, but that's where I like to visualize. All right, we have this, so now we can do our integral. So mu of y given x is equal to the integral over the range of y. The range of y goes from 0 to infinity. The value y, the joint density, x e to the minus x e to the minus xy, divided by the marginal density, e to the minus x dx. Please keep your dx's and dy's very, very carefully managed. This is dy, not dx. Okay? When your calculus teacher said, make sure you put the dx there, and you said, yeah, but we all know what I mean. Now I really don't know what you mean. You must know what you mean when you're writing these. Don't drop your dx's and your dy's. All right. We can do this integral, right? We're up for it. E to the minus x cancels on both sides. X is a constant, so let's just clean this up a little bit. I have an integral from 0 to infinity, y e to the minus xy dy. Maybe you already know what this is off the top of your head because you know the expected value of an exponential random variable, but if you didn't, you can do a trick. Well, you can. What's the trick?
Because one of the pieces of the parts is a polynomial, so it's going to differentiate down to 0.
Yes, we can do integration by parts if that's what you mean by the trick. Yeah, we can.
No, it's like the table, and then you don't even have to do integration by parts. It's kind of mindless.
You'll have to show me after what you mean by the table.
No, the tic-tac-toe one, where you go down and eventually go to 0, and you just do the diagonals.
I mean, I agree with you that we're going to get it's going to be a very easy integration by parts because you integrate this and you know how to integrate and you differentiate that and that differentiates to just dy.
If it were y to the 5th, you would want that integration.
Because then you wouldn't have to do a whole bunch of algebra. Fine, you guys.
The plus minus, plus minus.
You'll show me how to do that. That's not something. Yeah, there's all kinds of. I mean, I just do it out.
It's cute.
But I'm sure there's a nice clean way of keeping track of it. Or literally observe. In the case of, in the interest of time, do this calculation at home, or observe that this is literally the exponential.
With the rate equal to x.
Yeah, with parameter either theta is 1 over x or x, depending on what you prefer. And this is the expected value of an exponential distribution. So let's do it at home. What you get is 1 over x. So, is the regression of y on x linear? No. Right? The regression curve, so the regression curve is this hyperbola, 1 over x. This is the value of x, and this is the regression curve mu of y given x is 1 over x. Hyperbole. Okay, in the right column. All right. Let's get to let's get one more regression curve. I do want to prove a theorem today, if possible. If not, we'll do it Friday. So here's another example. Since we have to have multivariate, let's do a multiple regression. So find a multiple regression of, let's do x2 conditioned on x1 and x3, where the joint density function of x1, x2, and x3, given little x1, little x2, little x3, is given by x1 plus x2 times e to the minus x3, or 0. This is if x1 and x2 are in the unit box and x3 is positive. Otherwise, it's 0. So I can no longer draw a picture for you of what this looks like. We would need a projection from 4-dimensional space. Our eyes can handle 3. But there's an x1 direction, an x2 direction, an x3 direction, and then the value of this thing. Okay? And there's I could do a density plot or something. So these range in a box, x3 ranges in 0 to infinity, but algebraically, okay, maybe geometrically we can no longer wrap our head around this. There's nothing funny about this algebraic. So we want the regression of x2 on x1 and x3. What will that be? It's an expected value. It's a conditional expectation of x2 given that we know what x1 and x3 are. What do we know about a person's weight given their age and income? Or whatever it is you're trying to model. So this is an integral over the possible values of x2 of the value of x2 times the joint density of x1, x2, and x3 integrated dx2 divided by what?
The joint of x1, x2.
dx.
The joint marginal of x1 and x3.
So if you integrate x2.
Yes. Does everybody see that? It's the joint marginal of x1 and x3 as a function of x1 and x3. If you treat x1 and x3 as one variable that just takes values in pairs of real numbers, then this is the same formula that we had before. Does that make sense? So first we need to compute this joint marginal. So joint marginal f of x1 and x3 given little x1 and little x3. What will that be? I want to collapse my surface now, or hypersurface, onto, the x2 variable. I want to integrate out the x2 variable. So it's an integral over the possible values of x2 of f x1, x2, x3 as a function of x1, x2, x3. d x2. I'm getting rid of the x2 variable. Does everybody see that? What's the range of the x2 variable?
0 to 1.
0 to 1. Can you see that that's a 2? I didn't zoom this in. Can you guys in the back see anything I'm doing? Jordan, you're supposed to be my point man. We good? We're good? Okay. I'll just zoom it in a little bit. All right. So this range is 0 to 1. And then I put in the values. So this is x1 plus x2 e to the minus x3 integrated dx2, okay? E to the minus x3 is a constant that pulls out. The integral of x1 plus x2, x1 is a constant, so this is just x1 times x2. The integral of x2 with respect to x2 is x2 squared over 2. I evaluate this from 0 to 1. At 1, I get e to the minus x3 times x1 plus a half. And at 0, when x2 is equal to 0, and even here, by the way, it's better to write x2 equals 0 to 1. Once you have lots of variables floating around, it's very easy to get confused about, am I supposed to set x1 to be 0 to 1 or which one? So it's x2 goes from 0 to 1. Okay, did everybody get this for their joint marginal density? E to the minus x3 times x1 plus a half. So again, think about what you've done. You have this space of the densities. You want to integrate out the x2 variable, then that's the thing you need to renormalize by in the x1 and x3 variables. So that's what's going to go in the denominator. The original joint density function is going in the numerator. We're multiplying by x2 because we want the expected value of x2 given the other two variables. Let's do it. Any questions? Everybody's following what I'm doing? Great. So, this joint marginal, or the marginal, the regression of, the multiple regression of x2 on x1 and x3 is the integral over x2. x2 ranges from 0 to 1. I take the value of x2, I multiply it by the joint density function, which is x1 plus x2 times e to the minus x3. I divide by the joint marginal, which is e to the minus x3 times x1 plus a half. And then,
cancel.
right, those are going to cancel, but I integrate with respect to x2, dx2. Okay? I'm going to slide this up so we can do the integral. All right. Gosh, this is going to be a horrible mess.
X2 is not a bottom.
No, it's not. It's actually very nice because we're integrating x2, and x2 is a polynomial. The complicated stuff is all constants. First of all, the x3's cancel. Second of all, this 1 over x1 plus a half is a constant that pulls out. All I'm left with is an integral from 0 to 1, and then x1, x2 plus x2 squared dx2. That's a very easy integral. 1 over x1 plus a half times x1 is a constant, x2 squared over 2 plus x2 cubed over 3, evaluated as x2 goes from 0 to 1. I have the same denominator, x1 plus a half. The numerator, when x2 is 0, this is gone. When x2 is 1, I get x1 times a half plus a third. And if I want to clean that up a little bit, I can multiply top and bottom by 2 just to clear that. Or 6, but let me do one step. If you want to multiply it by 6, you can. If you don't like having a 2/3 in that. That's it. Where's the x3? How come it's gone?
They're independent.
Look back at the original function. It's not independent of x1, but x2 is independent of x3. Okay? So this is independent of x3. If the conditional expectation comes out not dependent on the variable, does it mean that the variables are independent? You'll have a homework exercise that shows no. Okay? The probabilities, if the probabilities themselves are always equal, if the conditional probability is equal to the original probability, then that's what it means to be, for those events to be independent. But you're doing an integral. It might be that the integral washes out a dependence even though there is a true dependence. Okay? On average, there could be no dependence by accident. Not by accident, I mean, that's just what happens, even though the variables are not independent. Okay? So the other direction, this implying independence, is not true. Hopefully you see what I mean by this. The marginal, okay, let me just write it in words.
Do we still care about the support of x1 or anything?
Yeah, we still care about the support of x1. This is all assuming we're inside the support. This is all if x1 is between 0 and 1. Yes, thank you. Otherwise, the densities are all 0. Yeah, let me just say that you will have an exercise. So if the marginal is independent of, let's say, x3, as it was here, that does not necessarily imply that the variables x2 and x3 are independent. But if the variables x2 are independent, that does imply that the marginal will be independent. Okay? All right. I would like to prove a theorem for you, if we can. Maybe we'll have time to state it, maybe we'll have time to prove it. So again, this function is linear or not linear? Not linear. Fractionally linear, but not linear. Bless you. It's linear as a function on projective space, but never mind. That's not what we're doing. It's not linear. So here's a theorem. Suppose I have a regression, let's say a univariate, a bivariate regression. And suppose this is linear. Okay? Assuming that it's linear, we can actually evaluate what alpha and beta must be from first principles. Then we know alpha and beta, these coefficients, can't be anything but the following pieces of data as a function of, I mean, I'll tell you what that function is. I could have just told you what it is, but then it seems kind of magical. We're going to compute what it is, and then we'll know what the answer comes out to. As a function of, well, what could be important things? We have the expected value of x. Let's give that a name. Let's call that mu, not to be confused with the regression mu. Certainly the expected value of y should play a role. Let's call that nu. If x has a large fluctuation, this might change. So let's capture the variance of x, bless you, as sigma squared. Let's say the variance of y, let's call that tau squared. And the other thing we should, of course, keep track of is the covariance of x and y. So covariance of x and y, let's call that, I don't have a good letter for this, C, covariance?
Or sigma x1.
Yeah, I'm trying not to burden, I mean, I could call this mu x and mu y and sigma squared x and sigma squared y. I'm trying to lighten our load. C, is C okay? Will you let me call it C? Yeah, I could call this mu x and mu y and sigma squared x and sigma squared y. Our notational load would be pet heavy. All right, that's the theorem. It's a vaguely stated theorem. I'm going to state it much more precisely once we do the computation and we solve for the values. So let's prove it, and then we'll figure out what it is that we're proving. Okay? All right, what is this margin? The marginal, by definition, I'll leave some room here. By definition, it's the integral over y of the value of y times the joint density f of xy divided by the marginal density of x integrated dy. And our assumption is that this is a linear function alpha plus beta x. I haven't done anything yet. Okay? This is the definition. This is the assumption, is that this function comes out to be a linear function in x. Here's the first step, the first trick. Let's multiply everything by the marginal density of x. Marginal density of x, marginal density of x, and integrate with respect to x. Integrate with respect to x, dx, integrate with respect to x, dx. So I don't know if you can see this. This is getting a little sloppy. Let's write it again. So all I want is this part of the equation. So all I'm saying is that the integral of x, the integral of y times the joint density divided by the marginal, integrated dy, times the marginal, integrated dx, is equal to the same integral, but now I'll replace the marginal by my knowledge of the marginal. The assumption is it's a linear function, fx x dx. I just rewrote what was above to make it a little bit more visible. Okay? So I took this inside function, which I assume to be linear, multiplied it by something and integrated. Multiplied it by the same thing and integrated. This marginal, as a function of y, is a constant. It pulls out. It pulls out and it gets hit with the same thing in the numerator, so it gets canceled out. Does everybody see that? And what's the integral of y times the joint density integrated out over all possible values of x and y? It's the, what is it?
Isn't it the marginal dense?
Um,
shit.
So I have all possible values of x and y. I take y and I multiply it by that and I integrate.
Conditional expectation.
It's just the expectation.
It's just the total expectation of y. These are all the ranges of y that can happen, including the ranges of x, but we don't care about the ranges of x, multiplied by y, integrated dx dy. This is just the expected value of y. This is just the expected value of y, which we gave a name to, we called it nu. Does that make sense? Let's look on the other side. What's happening here? I have alpha times the integral of f of x dx.
So just the expectation.
Well, alpha is a constant. This is a probability distribution.
Expected value of alpha.
Yes, but what's the expected value of alpha? Okay, fine, yes?
Alpha. Fine, yes. Expected
Yes.
value of alpha.
The expected value of alpha is alpha. The point is this is a constant alpha, because this integral is 1, and then plus beta times x.
The expectation.
So that's just the expected value of x, which we called mu. Does everybody see that first step? Let me save this for later. Okay? Everybody see that? Well, that doesn't help us solve for, I mean, what we know is that alpha plus beta mu is nu. That's great, but there's two unknowns and one equation. We need another equation. Let's go back to the beginning. Remember what we started with was the fact that the marginal, which is the integral over y, the conditional expectation, which is the joint divided by the marginal, dy, is equal to, leave a little more space this time, alpha plus beta x. This is, again, our starting assumption. What we did last time is we multiplied by f of x on both sides. Fx of x, the marginal distribution of x. We multiplied by dx and we integrated. Of course, if we do that, we're not going to get anything new. This time, let's multiply by an extra factor of x and then integrate. Okay, let's analyze this side. This is not a function of y, so it cancels off the denominator and the numerator. Everybody see that? And now I get an integral over all values of x and y, x times y times the joint density of those values. That's the expected value of
Joint density. No.
the variable x times the variable y. Right? That's what it means. This whole thing is the expected value of x times y. Right? Everybody see that? What does it mean to take the expected value of x times y? You have some joint density of with what probability these variables will take these values, and you multiply them by the values they took, and you integrate over all possible values.
So it's a C plus mu nu in our notation?
Yes, exactly. So let's work out what that is. Remember what the covariance is. The covariance of x and y, I mean the definition is it's the expected value of x minus its mean times y minus its mean. That's just the definition. But you can simplify it as, let's multiply all this out. You get expected value of x times y. Minus mu times the expected value of y is a minus mu nu. Minus nu times the expected value of x is a minus mu nu. Plus a mu nu gives you minus a single mu nu. Mu nu. Right? The expected value of x minus the expected value of x. The expected value of x times y minus the expected value of x times the expected value of y. That's the covariance. This is not the definition. Well, it depends on who you talk to, but for me, this is the definition, and this is the calculation. But it doesn't matter, because that expected value, we gave the covariance a name, we called it C. So that expected value is just C plus mu nu. Right? I bring that mu nu to the other side. Does everybody follow that? This is the covariance by definition, by calculation, and we've got the expected value of the product, so that's equal to the covariance plus the product of the expected values. So far, so good? On the other hand, let's look here. Alpha times x times the density integrated is
Times the expected value.
alpha times the expected value of x, which is mu, plus beta times the expected value of x squared.
So it's sigma squared plus mu squared or something?
Exactly. The expected value, remember what the variance of x is. The variance of x is the expected value of, it's the covariance of x with itself, x minus mu squared, which when you do exactly the same thing as we always do, is the expected value of x squared minus the expected value of x squared. The variance we called sigma squared. So the expected value of x squared is sigma squared plus mu squared. So this thing, let me just put it in, sigma squared plus mu squared. Does everybody see that? We are almost there. This is page 6.
So the point is we now have enough constraints on alpha and beta.
We have two linear equations. Here's one linear equation on alpha and beta, and here's another linear equation on alpha and beta. This is linear algebra. Actually, it's baby linear algebra. It's much easier. The two equations that we have to solve are alpha plus beta mu is equal to nu. I'm pointing to where you can't see. I took that first equation, alpha plus beta mu is equal to nu. Just rewrote it here. And the second equation, which we just derived, is right up here. Is there any nice way to simplify this? Not really yet. So here we get mu alpha plus sigma squared plus mu squared beta is equal to C plus mu nu. Did I miss something? Mu squared, thank you. That 2, there is a 2 there, but it didn't come out thick enough. All right, you could do this as a matrix and invert, but actually it's simple enough to multiply the top by what, negative mu or something, and add. Let's multiply the top by negative mu. Can I just do it right on the equation? Will that confuse people?
No.
Let me do a separate calculation. Minus mu squared beta squared is equal to minus mu nu. Just multiplying everything by minus mu. And now I can add these two. The point being that the mu alpha and the minus mu alpha cancel. I just get something in beta. In fact, the mu squared beta and the minus mu squared beta cancel. I just get sigma squared beta. So this tells me that sigma squared beta is equal to, and if I add these two, I get, bless you, I just get C. Does everybody see that? Okay, so beta actually comes out kind of nice. It's C over sigma squared.
Yeah, alpha.
And now alpha is a simple computation. So alpha is equal to nu minus beta mu. And beta, we know what that is. So this is nu minus C minus mu C over sigma squared. So these are this value of beta and this value of alpha are the two values. Now we can state the whole theorem. So the theorem is if the regression of y on x is linear, then that linear function, mu of y on x, is actually alpha nu minus mu c over sigma squared plus beta c over sigma squared times x. And we can clean this up a little bit. Let's put the nu to the other side, since that was the expected value of y to begin with. Now this is the conditional expectation of y. And let's pull the c over sigma squared together, and we get x minus mu left over. If your regression comes out linear, then y minus its expected value, or the conditional expected value of y minus its total expected value, is equal to the exact value of x minus its expected value with the covariance divided by the variance of x. Nice and clean. Okay? So if it comes out linear, then there's only one way that that linear relation, there's only one way that that linear relationship can hold, and it's in terms of the covariance, the variance, and the two means. And we are out of time.